Good morning, everybody. I'm very glad to introduce the speaker of today, Lorenzo Amati. I now briefly resume his career. Lorenzo took his degree in astronomy from the University of Bologna in 1991. Then he obtained his PhD in 1999 from the University La Sapienza in Rome. And since 2017, he has been dirigente di ricerca at the Bologna Osservatorio di Astrofisica e Scienza dello Spazio of the Italian National Institute of Astrophysics. His main research field is high-energy astrophysics, in particular the observation and physics of gamma-ray bursts and their exploitation from cosmology. His work is also focused on study and development of next-generation GRB monitors. He started his career in the Beppo Sachs team in Rome with Enrico Costa and then in Bologna with Filippo Frontera. He has been involved in some of the major discoveries on GRB by the Italian-Dutch satellite Beppo Sachs, in particular the Amati relation, a relation between the spectral peak energy and the total emitted energy. Since 2016, he has been leading the Theseus project, a space mission concept focused on the study of GRBs and high-energy transient phenomena for cosmology and multi-messenger astrophysics. Theseus has been selected by the European Space Agency in 2018 for a Phase A study, and again it has been selected in 2022 as a candidate for launch in 2037. I let now the floor to Lorenzo that will tell us about the Theseus mission. Thank you very much.
Thank you. I'm trying to move this video thing. Okay. So thank you very much, Piano. Thank you, everybody. So it's my pleasure to be here, talk about Theseus in this institute where I had my PhD in the Beppo Sachs team. So which was a big opportunity. So thank you very much to Enrico, Marco, Paolo, and all the colleagues of the Beppo Sachs team. So today I will talk to you about the Theseus mission space concept, which, as the name of the mission says, Transient and High Energy Stellar Universe Surveyor, is a space mission concept aimed at dedicated to high energy transients, especially gamma-ray bursts, that we will show in a while. And is carried on since many years by a large European consortium led by Italy, Germany, UK, France, and Switzerland, with contribution of many other countries you see the plan here. So, let me just a summary of the programmatic history of this mission concept. So Theseus was submitted in 2016 in response to the call by the European Space Agency, ESA, for the fifth medium-sized candidate mission. It was selected for a 3-year Phase A study from 2018 and 2021 in competition with other two missions, the Vision, which was a mission to Venus, and Spica, which was a larger infrared observatory in collaboration with Japan. The study was actually successful. At the end, the result choice based on the balance of the program or scientific program selected Envision, but given all the great experience we gained with the 5 Phase A study, we submitted again in 2021 the project to ESA in response to the call for the N7 mission, which is actually the 6th medium-sized mission, because it's called N7 because the 6th was cancelled from the ESA program. And again, we were selected in 2022 among the 5 missions who went through a Phase 0 study, so a preliminary before Phase A study. And last November, we were selected again for a new Phase A study, which will go on from January this year up to June 2026 for a possible launch in by 2037. So here you see the main contribution. The name of the leads. So the lead proposer, myself, and the lead proposer on behalf of INAP and Italy and DARGE, of course. So Italy has a leading role in the mission. You can find in the literature many papers on Theseus, on the science case, science requirements, the instrumentation, the mission profile, and the expected performances. Here I mentioned some. You can simply search Theseus in the ABS, you can find a lot of literature. And also we have a very nice website managed by University of Geneva, in which you can find more information and a lot more. So just before beginning, talking about the science core objectives of TCUS, as I mentioned, TCUS is a mission dedicated to gamma ray burst, high energy transients, okay? But as we know, if we have a look at these science programs, so the missions that were selected in the so-called Cosmic Vision program, and now in what is called the Voice 2050 program, the program is based on three kind of missions, like the T-shirts, so small, medium, large. This is mostly based on the budget that is put in these missions, and this is reflected into the capability of the mission, the science objectives, and the actual size of the mission. So a medium-sized mission like TCUS, like Euclid or Orbiter, Plato, the budget is around 550 million euros, the cost to ESA, just to give you an idea. But if you have a look at the missions that were selected and their core science case, you can see that actually, if you want to sell a mission to a big space agency like case on your sources of interest, or you want to understand exactly the physics of the mission of HN, the role of the magnetic field, what are the mission mechanisms of gamma ray burst from the missions, etc. Very interesting topics, but you have to resonate to very high level teams for modern science. So if you have a big look at this, you can see that most of these missions, if not all, resonate with main keywords, which are cosmology, fundamental physics, and life in the universe. So when ESA and NASA select a mission to study Venus or Mars, this is not because they're interested in understanding exactly the composition of the atmosphere of Venus or the soil of Mars and so on. This is interesting at some point, but it's not main science team. The main science team is life. So we want to study the planets that explore the solar system, the ice moon, Jupiter, Saturn, exoplanets, again, because we want to investigate life, the habitability of the universe, the evolution of life, the possible existence of life beyond it. And the same for other missions. If you have a look also, for instance, a great X-ray observatory like Athena, it is not proposed as a general X-ray observatory. It is proposed as a mission for the hot and energetic universe, so cosmology, fundamental physics, multi-dimensional astrophysics, gravitational waves, fundamental physics again. So life, fundamental physics, cosmology. So this is very important. And this is why the core pillars of TCUS are not simply investigating gamma ray burst, which would be a very interesting by itself topic, but it is exploiting gamma ray burst for exploring their universe. So if you put a gamma ray burst that has been shown a while in a cosmological context, you can see you have these hugely bright beacons that explode up to the epoch of the formation of first stars, first galaxies, so right the epoch that JWST is now investigating, which is raising a lot of interest. And so gamma ray bursts are expected to be a key observable for understanding the first phases of the universe, as well, you know very well also that gamma ray bursts are also a main electromagnetic counterpart for gravitational wave signals produced by merger of neutron to black holes. And so and hence fundamental physics. Of course, such an observatory capable of achieving all these great goals would also be a great observatory, a great transient machine that would be capable of detecting, localizing, characterizing in a multi-wavelength fashion most classes of gamma ray burst and also IAPS. So it would be also a general part of the observatory. So just for those of you who are not confident with gamma ray burst, I think most of you, if not all of you, very classical pictures here. So gamma ray bursts are sudden burst of hard X-ray, soft gamma ray radiation discovered by chance in the sea, serendipity in the 60s by military satellites, when it was understood that they come from the sky. So the ball was given to the astrophysicists who started to study for many decades. This phenomenon remained mysterious because a satellite in lower orbits, so if you put a scintillator counter in lower orbit, you measure more or less one gamma ray burst per day coming from random direction in the sky at random time. from random directions. So it's really, and in a few seconds or tens of seconds or a fraction of a second, so you have a bimodal distribution of gamma ray bursts. You have short ones lasting less than 1 second down to a few tens of milliseconds, long ones lasting typically from a few seconds up to several minutes. For many tens of years, so up to the end of the 90s, this phenomenon remained mysterious. So up to 1997, we still didn't know if this huge flashes of gamma ray radiation came from cosmological sources or a halo around the galaxy, or even from the outer solar system. Then a key discovery was, of course, the multivalence emission that followed the gamma ray burst, which is the main discovery by the Beppel-Sachs mission in the X-ray, allowing the discovery of optical, radio, near infrared. So it was discovered that after the bursting the convex gamma rays, there is a multivalence fading emission, which is called the alpha, which is also key for exploiting gamma ray bursts for cosmology, multi-messenger astrophysics. So starting from the 1997, there were huge observational efforts put in understanding gamma ray bursts from space, from the ground, joined with theoretical efforts. Now we have a picture, standard pictures of what most of them are very high redshift, so actually other than 0.1. Long ones, you see the gray shaded distribution here, have been detected up to actually more than 9, which means a few 100 million years after Big Bang. Instead, short ones have a lower redshift distribution, but many evidences support the idea that most of gamma ray bursts, at least most long gamma ray bursts, are produced in the core collapse of very massive diffuse stars. Short gamma ray bursts, the main fraction of short gamma ray bursts, are produced by the merger of neutron star or neutron star black hole binary system. As you can see already here, but this is also sketched better here, independently on the progenitor. So independent if the progenitor is a very massive star, core collapse of very massive star, or is a merger of compact objects binary system. We expect before that the engine, so there is the progenitor, very different, but the central engine in both short and long gamma ray bursts can be a black hole, a newly formed black hole, accreting matter around it, and then producing this ultra-relativistic jet that produces the RDX of gamma rays, so the typical gamma ray burst, through either internal collisions or internal shells, so shocks, or dissipation of magnetic field, and then after the emission, there is also the possibility, highly investigated, that instead of a black hole, it is formed a supramassive, highly spinning, highly magnetized neutron star, in which case, of course, the expression mechanism of the energy, the production of the jet is different, but at the end, you have a similar phenomenon. You can try to distinguish between these two central engines based on the properties of the prompt emission. But this is not the purpose here, but this is just to put all of this in context. So as said, one of the main core goals of this use is to fully exploit the long gamma ray bursts, so those that are produced by the core collapse of very massive stars, for exploring their universe, as I mentioned before. So we have this hugely luminous phenomenon. We know that gamma ray bursts can dissipate in a few tens of seconds, in a few minutes, as much energy as is dissipated by a sunlight star in 10 billion years. So we are talking about related energy of luminosity of 10 to 51, 10 to 52 per second. And actually, they can, thanks to this, and thanks to the fact that they emit most of their radiation in X gamma rays, they can be detected up to the so-called cosmic dawn. So we know that after recombination, when the CNB is released, let's say, for several million years, 10 million years, the universe is mostly composed by neutral hydrogen. There are no stars, galaxies, so it's called the dark age. And then first stars, for the galaxies start to form, the universe starts to be reionized. We think, thanks to the ultraviolet photons emitted by the first population of stars, matter of investigation. And this epoch, which is from a few tens to a few 100 million years after the Big Bang, so down to redshift of more or less 6, it is called the cosmic dawn. And we have gamma ray burst providing a unique tool to explore this very early epoch of the universe. And just to give you a flavor, the magic power of gamma ray burst, again, it is true that HST, through its frontal field and through gravitational lensing, could detect some very redshift galaxy at this very early epoch, 8, 9, 10, 200 million years after the Big Bang. But what you can see, redshift of 9.2, 9.4, which is actually 400 or 500 million years after the Big Bang. And this is the direct image of the consequence of an exploding star at such an early epoch. So thanks to gamma ray burst, we can detect and localize and identify an exploding star. So a star, one of the first stars ever generated in the universe, directly, because we can catch the near-infrared emission produced by the jet that is emitted by the collapsed core of the star, and which produces, as I mentioned before, through the interaction of the jet and the interstellar medium, this near-infrared emission. So, given that we know by studying the star formation rate evolution compared to the redshift distribution along gamma ray burst, we know that most of long gamma ray bursts are associated to the core collapse of massive stars. These stars die where they were formed, so they are traces of star forming region or star forming rate. Because we have a look here, this is quite a few years ago, before JWST, the star formation rate evolution in the universe, which is especially uncertain at redshift higher than 6. Redshift 6 is more or less the first billion years of the universe, which is actually the epoch of interest, because it is the epoch there were, and if the ultraviolet photons of these stars were enough to produce cosmic organization, otherwise we have a main issue which may involve standard physics moments. You can see this is there is a large uncertainty, blue regions are obtained by the few very redshift galaxies that were detected by HST, and assuming a given shape of the luminosity function of primordial galaxies, which we don't know, because of course any optical telescope, and this is true also for JWST, the telescope, has a threshold, has a sensitivity limit. Whereas with a statistical sample of 2 times of gamma ray burst, this is an example, this red crosses, it will achieve such a great accuracy compared to the uncertainties that you get on the star formation rate if you base on the extrapolated luminosity function star formation rate from the few very redshift galaxies. And this is because gamma ray bursts occur in a galaxy, very redshift galaxy in this case, independently of the luminosity of the galaxy. So you can pinpoint the existence of a galaxy, you can unveil, and you can see this much better here, you can unveil the bulk population of the invisible low mass part, or to be invisible to the JWST, because the occurrence of a gamma ray burst does not depend on the luminosity, on the mass of the galaxy, whereas the detection of a primordial galaxy by JWST, by HST, JWST depends on this luminosity. And this is a sketch, this is the depending aspect of a gamma ray burst near the planet. And these are images taken by HST after a few months. So when the afterglow of the gamma ray burst faded away, you point the HST, very sensitive instrument, of course, and you see nothing. You see nothing. This is a clear demonstration that it was only thanks to gamma ray bursts, our capability of detecting, localizing, and following in the optical infrared this gamma ray burst, that we know that here, in this direction, at this redshift, there are 6 primordial, weak, low luminosity, low mass primordial galaxies, which were beyond, so below the detection sensitivity to HST. And we think that this is the bulk of the population of primordial galaxies, which cannot be unveiled by HST. And not only thanks to gamma ray burst, we can unveil, localize, and do a statistical census of primordial galaxies, but through a Thorson spectroscopy of this light that is the after of gamma ray burst. So if we are fast enough to point, fast enough means 10, 12 hours, not minutes. We can point ELT, or now ELT or SETI test, so after 12 hours, 24 hours, in the direction of the article and catch that payload, you can do this kind of spectroscopy, and of these invisible colors, not only we know that they exist, how many there are, at what ratios they are, but we can learn the mechanicity, the neutral hydrogen fraction, the features of the intergalactic medium, so the ionization status of the intergalactic medium around this primordial galaxy. So it's a unique way of detecting, characterizing primordial galaxies that are below the detection threshold of any optical infrared telescope, and also studying directly the evolution of the cosmic realization. As I mentioned before, even GWST has a limiting sensitivity, even GWST. So even with GWST, if we want to, we need to extrapolate from brightest galaxies what is the population of all mass groups. We have to make assumptions, and this is why there is still this large uncertainty in star formation rate evolution in the population of primordial galaxies. And moreover, these are we know the recent results of GWST, which are amazing. They are showing they're solving some issues, but they are putting forward more issues. So from one side, the lower limit to the star formation rate evolution very aggressive that you can derive with GWST is still a lower limit because you need to extrapolate. Is consistent with what with the extrapolation from the HST results, but also there is this interesting apparent excess of luminosity galaxies. And just to conclude this aspect of the science case, and this is the sketch that I showed before. So these were the uncertainties in the star formation rate evolution based on the Q variation. And these are regions are still the region of uncertainty. So despite the very sensitivity of GWST, GWST is putting all of this at higher ratio, but the uncertainty remains the same because you still have to make assumption on the bulk of the population of low luminosity, low mass primordial galaxies. And this is something that can be studied on this thanks to gamma ray. So this is quite well known by cosmologists. The main issue is that if we have a look at the distribution of gamma ray bursts, we can see that we have started many efforts from ground, from space, for studying gamma ray bursts. We are still stuck to less than 10, 7, 8 gamma ray bursts detected at very ratio. So I mean ratio higher than 6, 4 billion resolution. So main goal of this is to fit this gap by putting here many tens or even 100 or more gamma ray bursts here to fully enable cosmology with gamma ray bursts. The other phase of the main core science of this use, as I mentioned at the beginning, is multi-messenger astrophysics. This is the beautiful observational picture that we got in 2017, 17th of August, 2017, where there was the first detection by LIGO Virgo of a gravitational wave produced by a neutron star binary system, so neutron star merging. Up to then, and even up to now, most signals detected by LIGO Virgo are from black hole binary mergers. This was from a binary neutron star system, and only a few 1.4 seconds after this event, from a region consistent with the gravitational wave signal, the GMD monitor on both fields detected a short gamma ray. So this is the first clear evidence supporting the idea that was carried on by many years, as I mentioned already before, that at least a fraction of short gamma ray bursts are produced by neutron mergers, which are expected, all of these systems, to produce detectable gravitational waves if this system, with the current sensitivity of the detectors, is at say 100, 200 megapascal at most. And actually this event was at around 50 megapascal. It was an exceptionally nearby short. Not only so, thanks to a very intensive follow-up campaign, it was also discovered that associated to this event, there was a fading in near-infrared emission. Here you see the curve, here you see the to understand that this emission was due to what is called the kilonova emission, the kilonova phenomenon, which is near-infrared emission produced by the radioactive decay of very heavy elements being formed in the very neutron-rich material left after the merger. So this also confirmed the conjecture that these sites, these mergers, are also the site of formation, a main site of formation of very heavy elements in the universe. So clearly, if we could get that up to now, we are sticking with only one. So because of the sensitivity of current gravitational wave detectors, and because of the limitations of current GRB detectors, maybe we are still not very lucky, but we are still stuck with only one gravitational wave signal from neutron star mergers associated to a gamma ray burst. But if we could get us, which is a goal of this use, many tens or hundreds of these associated detection, we could of course put together the information we can get from gravitational waves and the electromagnetic domain, and also the redshift, the host galaxy identification that comes thanks to the localization of the gamma ray burst and the follow-up of the gamma ray burst, which you need. We could do a lot on the physics of these systems, the neutron stars, the jet, the cosmic photosynthesis of very heavy elements, and also interesting multi-messenger cosmology. I will get back to this later. So, in order to achieve these breakthrough goals, the mission concept of TCUs is similar to mission concepts which are being proposed, developed worldwide. So TCUs, let's say, is the most advanced next generation gamma ray burst mission among a worldwide idea of the community that is to overcome the limitation, the current limitation of GRB detectors in space, follow-up strategies from the ground. And so first of all, we have to increase substantially our capability of detecting and localizing very high redshift gamma ray bursts of cosmology, but also value of axis nearby of gravitational wave detectors. We can detect very nearby gamma ray bursts. Most of them are collimated, we know, have a high degree of collimation. If the closer they are, more of axis we detect them. So it's a very soft emission. In practice, we need to extend the energy band down to very soft X-rays with respect to the current gamma ray burst detector, which mostly work about 10 kV. So, for instance, this is something that partly is being done by Einstein probe. The other main limitation preventing us to measure the redshift of gamma ray burst. So we have to think that there is the Swift satellite, Cosmos Wind, the Fermi GBM, many other GRB satellites work. There are many robotic telescopes on the ground dedicated for what of the gamma ray burst detected by these observatories. There are many observation programs approved at large telescopes for the follow-up of gamma ray burst. Despite all of these efforts, we are still stuck with measuring the redshift of gamma ray burst only for 25% of the overall population. So there is another main source of inefficiency in the follow-up, especially for high redshift gamma ray burst in the near infrared. So this is why the idea of this use is to put the follow-up directly on board. So to keep the spacecraft with the possibility of promptly pointing an infrared telescope, which is included in the payload, thanks to the fast viewing capability of the spacecraft. So more specifically, the payload, so the instrument suite of TCUs, carries on board two sets of monitors. One is the soft X-ray imager, which works in the very soft X-ray, so allows the extension to very soft X-ray, so the extension in energy band and sensitivity. Microphore optics in so-called lobster eye configuration, which allows focusing soft X-ray over a huge field of view. Because when we think of an X-ray telescope, focusing telescope, large field of view is already half of a degree, 1 degree is huge. Here we have a technique for focusing X-rays over several hundreds of square degrees. So each of these cameras has a field of view of 125 stellar. Nevertheless, we need, in order to enable the detection localization of various class of gamma reverse, the redshift, short gamma reverse for multi-universal physics, ultra long, X-ray test, or plectron and many transits. We need another monitor, which is the ZSense gamma ray imaging spectrometer, which, by the way, is the full Italian instrument, which is based on silicon detectors coupled with crystal scintillator. So it's based on these bars. You can make a position-sensitive pixelated detection plane. You can use the coded mask technology, and you get a GRB monitor with unprecedented energy band from 2 keV up to 10 eV with 500 square centimeter effective area down to 2 keV and down to 10 eV, which if you compare with the BAT on board the Swift, which is limited to 150 keV, the GPM on board Fairly, which is limited from 10 keV, so it cannot go down 10 keV. This is really covering, feeding an observational gap. And the infrared telescope is a small 70 centimeter near infrared telescope working in a classical infrared range using paradigm detectors with a large field of view, 15 by 15 minutes, so to take into account the limited location capability, especially of physics. So here, just to say a few words more specifically on the instrument, but just very quickly, this is the concept behind the lobster eye concept, as I mentioned before, our software and imager, which is exactly the same technology that is used now by Einstein probe, exploits this micropore-optics when you can have no reflection, one reflection or double reflection of any ray, and so you have that a point source is produces, is focalized as a cross. So here the idea is to exploit what nature already discovered many years ago, which is the same concept that is used by nature for the eye of the lobster, which needs a much larger field of view with respect to us, for instance, to monitor the enemies trying to eat the lobster. And this is the sketches, as I mentioned at the beginning. TGS already went through a full phase A study as a candidate M5 mission. So we are in our hands already. Design, mechanical design, thermal structure analysis, any kind of model documentation in our hands. So these are just examples of the mechanical drawings. So these are engineeristic drawings for the SXI camera. And this is just to compare the capability of such a large field of view focusing instrument compared to classical telescope like XMM or Chandra. So, of course, they are much less sensitive than XMM or Chandra, but thanks to the huge field of view, the thrust, which is the efficiency in surveying the sky, is much larger. Here, again, I focus more on the GIS, our instrument. This is a sketch of the detection concept, again, silicon detectors, which were developed by a large collaboration in Italy, involving the NFM, ENAF, and many institutes, which were proposed by this kind of detector, working from 2 keV to, let's say, 30 keV. Very good timing, so over 50 microseconds, very good energy solution. You can be any size that you want. In the case of the GIS that pixelated, they are half of a centimeter squares. For the hard-X gamma ray radiation detected by a crystal scintillator part, which is coupled with these two silicon detectors. And this provides the capability, thanks also to the coded mask for the imaging, we understand the capability of the GIS, which is the hugely energy band, the high effective area through the whole energy band, the excellent timing, and also the capability of localizing sources better than 15 minutes, combined with a large, very large field of view. You see the IAPS, the SXI, and the GIS, the image field of view. The GIS has an imaging capability up to 160 keV. Above it becomes transparent, the mask, so it has a full open sky field of view. But you can see comparing the criteria of the disease to that of that with that of the here, the main difference, filling the gap below 10 kV, which is key for high ratio gamma reverse because the disease can detect also many ratio gamma reverse and also keeping an excellent effective area up to 10-20 dB. Okay, the infrared telescope, I think it can go faster. It works in 5 filters. Here, these are the magnitude around 21. The sketch, it's a very compact design. It's a so-called controflex design because a primary mirror of 70 centimeters. The focal length is also more or less 70 centimeters, the distance between the two primary mirrors. And so it is designed to keep it compact for payload accommodation and to have a large field of view as much as possible. And the main feature of the ILP is that it will not only have the sensitivity gamma reverse detected by monitors, following the zoom of the spacecraft to point the telescope in the direction of the gamma reverse within a few minutes, but it has also the possibility, upon the mandatory requirements, that it will be able to measure on board the redshift. So identify directly on board the redshift of the gamma reverse through photometry. You can see here or here. You can see the advantage of gamma reverse is that they have very flat spectra, very simple, powerful spectra, which are flat in such a narrow range, with a very, very sharp line and drive cutoff. So very easy to measure photometry for gamma reverse. And you can also do with the low resolution spectroscopy of 400 more or less resolving power, which you can use to measure also lines, line alpha feature, so to confirm the redshift, but also to do already autonomously the characterization of the host galaxy of this very redshift gamma reverse. So these are the sketches, not only the sketches, the output, some of the output of the industrial studies that were appointed by ESA during the previous phase A. As you may know, for each candidate, ESA selects 2 industrial primes which carry on industrial study of the spacecraft, of the payload accommodation. For this use, they also study the telescope of the RT 4 and 5. You can see the 2 solutions proposed by the 2 industrial primes, which were ABS Space Germany and Thales Spazio. The spacecraft more or less would weigh around 2 tons. This is suitable for launch in low Earth orbit, low inclination, low Earth orbit. Vega, in the case of M7, should be a Vega C, Vega E launcher. The orbit is chosen to be low Earth, near the equatorial, to keep the background in the monitors as low and as stable as possible, and also to prevent too high radiation damage, especially for the silicon detectors. So thanks to this combination of instruments and mission profiling, as shown here in this spectral mechanics or spectral hardness intensity diagram, this use will be able to detect, localize, measure the redshift, and provide a multivariate characterization of any class of gamma reverse. Short, long, very redshift, ultra long, X-ray flashes, anything. And plus many other classes of parameters, of course. And you can see here, this is the region of the discovery display, for instance, by the GBM. And here is where the bulk of very redshift gamma reverse are expected to lie. And all this region will be accessible by this use. So to convert these capabilities into results from very redshift gamma reverse and exploration of the universe, this is again the current situation where distribution in redshift is inversely versus redshift, but especially if you put the current distribution in redshift of long gamma reverse in the cone, you see that above this line, which is redshift of 6, which is 4 billion of years, we have this, in the last 25 years, you could put less than 10 gamma reverse. And with GEOS, you will obtain this. So you will obtain detection, localization, redshift measurement, and characterization of those galaxies of many hundreds of gamma reverse, and at least 40, 50 in only 3.5 years of operation. 3.5 years is the nominal duration assumed by ESA, because they have to assume a nominal duration, but Theseus could live like Swift for 10, 15, 20 years. So there are no consumables, no re-energy systems that at some point will not work. So reasonably, Theseus could work for 10, 15, 20 years. But I don't know what. So put here, this is just a very, very minimum performance. And I have to say, this kind of performance is not just simulation by the Theseus team. This comes from very tough simulation, very realistic simulation, and conservative simulation performed by ESA, that developed a very sophisticated mission observation simulator, which simulated the whole operation of the spacecraft, the operations, any constraint in the pointing of the infrared telescope, the thermal control, the field of regard, the pointing, different pointing strategies, the expected performance of the instrument, and so on. So this is a very, very minimum performance. It's already great, at least 50 very rare gamma bursts compared to, so this is 15 per year, so this is 12, 15, more than 15 per year compared to 0.3 or less per year, which is the current rate. On the multi-messenger side, I said before, this is the beautiful picture we got, and we hope to get more of these events in 2017. We hope to have, with the new run of the gravitational wave detector that is ongoing, at least one or two more. But this is very difficult, again, because of the horizon, very nearby horizon of the gravitational wave detectors, and because of the, because of the limitation of current gravitational waves regarding current GRB detectors. Instead, Theseus will be capable for many events to do all of it by itself. So to detect and localize the short gamma ray burst associated with the gravitational wave, possibly detect and localize the soft X-ray emission, which is expected to be associated with these events, and also with the infrared telescope, detect and characterize for the nearby events the kilonova emission or the afterglow emission for the other events. So this is an estimate that was done in collaboration with the Einstein telescope. Of course, we have a very tight and strategic synergy and collaboration with the Einstein telescope. Collaboration and projects, which are contributing a lot in doing this kind of estimates. So in 3 years, we expect more or less 70 simultaneous detection of short gamma ray bursts by Theseus and gravitational waves by Einstein telescope. And this is not unexpected, because given the horizon, so Einstein telescope would be capable of detecting gravitational wave signals from neutron star mergers up to redshift of 2.53, and all the short gamma ray bursts that we know, we can detect now, at least, have a redshift below, so they're all up to 3, more or less, almost all. So we expect that for each short gamma ray burst detected by Theseus, simply detected by Einstein project. Moreover, again, given that many of these, most of the gravitational wave detection will be from mergers at very high distance, at which you cannot detect the kilonova and infrared with the optical infrared campaign, the gamma ray burst would be likely the only possibility for detecting an electromagnetic counterpart of most gravitational signals detected by LIGO. By Einstein telescope in the future. So this is again a summary of all the science you can do, but I just focus a bit on the cosmology, because if we actually will be able to get many tens, at least 20, 30 tens or even more, of the simultaneous detection, gravitational wave, gamma ray burst, and hence identification of those galaxies, measure of the redshift, we can put together this information, because we have the modeling of the gravitational wave signal that gives you the distance in a cosmologically independent way. It gives you the distance is a parameter. And then you have the redshift from the electromagnetic identification of the counterpart of those galaxies. And when you have a source that produces the distance in the redshift, you have a beautiful cosmological probe, beautiful probe, very powerful for measuring the constant, for measuring cosmological parameters like for instance, is the density of dark energy in a given parameterization. You can test different cosmological models. You can actually see if there is or not an evolution in the data. So if the lambda CDM is confirmed, or if this lambda is not lambda, but it's something different. For instance, an evolving dark energy or something different. As there are some hints, you know, from the dark energy survey recent results. So you can even, just to mention, we can even be more optimistic, because in this estimated detection rate, we assumed only short gamma ray bursts, but we know now that there are at least a fraction, or at least a small fraction of long gamma ray bursts are produced also by neutron-star mergers. There are two cases in the recent years in which there is clear evidence of association of long gamma ray bursts, technically long, with kilonova emission, which is expected from neutron-star mergers. Given that long gamma ray bursts are much easier to detect with respect to short ones, which means that if a fraction of long gamma ray burst is produced by neutron-star merger, our expectation for the simultaneous detection of gravitational waves can be even more optimistic. And just to mention, up to now, we focused on short gamma ray bursts, on neutron-star mergers, because these are the most prominent signals that can be detected by current gravitational wave detectors. But of course, there is a plethora of other possible sources, also unexpected transit, that could be unveiled by a machine like this used in association with gravitational waves. So just to mention, this is that when we will get with this use a sample of many hundreds or 1,000 or more gamma ray bursts with measured ratio, with very well measured spectra, timing, and so on. So we could do a lot on the physics of gamma ray burst. This is comparing a spectral measurement by 3 GPM with what we expect to do. So an extension of by 2 orders of magnitude in the soft allow you to detect breaks to text emission models, which are still very uncertain, for instance, and go quickly because it's quite late. But also it is also very interesting that with GRBs alone or with gravitational wave, you can also do not only extreme physics, not physics. For instance, the fact that the GRBs came 1.4, 1.7 seconds after the gravitational waves is already setting a very big limit to the difference in speed between gravitational waves and light and radiation, which is of course another fundamental test for the prediction of general relativity. I do not go into details. Of course, this 1.7 may be due to the time to intrinsic effect, the time that the jet needs to be produced after the merging, the time that is needed by the jet to escape the neutron-rich material around the black hole of the neutron star producing the jet, the time that is needed by the jet to dissipate the energy to produce the burst, and also our sensitivity of the instrument. So this can set already a very deep limit, even though we consider all these other effects. Another interesting possibility with this sample of tissues is that we could have in our hands the ideal phenomenon sources to test Lorentz invariance vibration, which, as you know, is a fundamental test for quantum gravity models. So different quantum gravity, different classes of quantum gravity models predict the so-called dispersion law. So they predict that the speed of light varies with the wavelength, the energy of the photons, and the effect that you measure is higher as the farther away is the source. So you need very far away sources, you need very bright sources with a lot of photons, and it is also proportional, the effect, to the different wavelengths and difference in energy between photons. So with GRBs, you have all of these. They are very far away, you have a huge amount of photons, you can detect them over several orders of magnitude in energy. So you have a perfect ingredients to at least set very deep limits or exclude, if not even confirm, some classes of quantum gravity models. More in general, as I already mentioned, this capability of species will allow it to detect, study, and characterize many classes of other energy standards in addition to the gamma burst. Of course, this is the sensitivity of the software image as a function of time compared to the time intervals And despite the fact of many classes, this is a guest observer capability. So we have in our requirements also that TCUs will also provide to the community a guest observer capability to use the SXI, the infrared telescope, and so on for dedicated observational programs. And of course, a key feature of TCUs, key asset, are the synergies, because under all these respects that I mentioned, gamma ray burst, energy transits, cosmology, especially multi-messenger astrophysics, is using synergy with all the very large facilities of the future that are being built for all the electromagnetic domains, so the ELT, OPLT, the optical and infrared, SKA in the radio, CTA for the energy, new antenna in the X-ray, and also in the multi-messenger domain, as I mentioned, third generation gravitational detectors like Einstein telescope, cosmic explorer, next generation neutrino detectors like kilometer cube net, and so on. All these facilities have this kind of science in their core science, but they need a transit machine like TCUs to fully achieve these goals. So I think that if my time is up, I would not, I think I can skip all the programmatic. I just mentioned the main role of Italy in the TCUs project. This is the payload procurement scheme. You see that the SXI is a responsibility of UK and Germany, with contribution of any other country. But this is full responsibility of Italy. And Italy is also co-PI with the infrared telescope because it provides the optical system, in addition to the Malindi ground station. So I think here I just listed the many institutes involved in the study of the GIS, ETINA, universities in Italy. Of course, we have an international GIS consortium involving Spain, Germany, Denmark, Poland, Norway, and Ireland. And for the IRT, which is led by France, we produced the infrared telescope. It's a novelty for M7. And the key actors here are INAF Brera Merate, Politecnico di Milano, Porto INAF Bologna, again, through the whole TCUs collaboration. Of course, there is a large scientific community behind TCUs inside TCUs community, the TCUs consortium, which is organizing several science working groups, which are very active. They are fundamental in building the science case, in interacting with these, with the science panels that evaluated the scientific impact of the mission, and also to coordinate with the science study team that was nominated by ESA for TCUs. So I think I advise all of you to have a look also at the TCUs website. If you are not still part of the TCUs consortium, please, you are invited to register. There is a very nice web.
Thank you, Lorenzo.